go live now, and Sao, you can check.
Okay, I'll check.
All right. Sahil, can you test? Is it reasonable?
Um, We're we're live.
Okay. All right. Hello, everyone. Welcome to today's brand new episode of Corecast. I am your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome, everybody, to a brand new exciting episode of Queercast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching this on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, ask us questions during the episodes when we get to them. Although there's a bit of asterisk, because sometimes we skip weeks here and there due to work schedules and whatnot. So small asterisk there, so you don't get me on that later. Anyway, so without further ado, let's get to it. So we had been talking a lot with the past episodes on the notion of time. Can you go backwards in time? The different arrows of time, and we've been talking mostly, I would say, like at a larger macroscopic scale. And we thought like today's episode would be great to look at time from the perspective of the quantum mechanics. And so we want to ask the question like, what role is time playing in quantum mechanics? So like how's time, like what is time in quantum mechanics like in some sense? And so I guess, Mikey, I'm just gonna pass this off to you first. Can you kind of explain, maybe if you know it, of course, like maybe the history of like how people's conception of time has changed? It's a loaded question. I'm totally putting you on the spot. You can say no if you don't know.
Yeah, I mean, it's just like in a very straightforward sense, like just naively, like if you take a class on quantum mechanics and a class on classical mechanics, like time is kind of enters in a similar way. It's just a parameter, right? You have some equations, and time is the parameter that dictates the rate at which things change, essentially, right? But there are some interesting differences between or the consequences of how time works in quantum mechanics versus classical mechanics. And to talk about those, I think I'll hand it off to Tim.
Yeah, I suppose we need to kind of go back to the classical realm when discussions like these, like arrow of time, first started. People got interested in this subject when they were studying things like heat engines and large scale system, and they come up with laws like the second laws of thermodynamics, where entropy is always increasing, and they kind of understand these arrow of time. And from the classical physics perspective, these can be explained by what we call chaos, classical chaos, where you can imagine particle in a box, and the particles are just kind of stumbling around left and right, left and right, left and right, and the pattern is almost totally unpredictable. And as such, because it's so unpredictable, we can approximate it statistically. And it also seems that because of this unpredictability, intractability, there's kind of this model that anything that could happen will happen because the particles are moving every which way. So you can kind of pick any particular configuration for these particles to be in, and eventually, if you wait long enough, all these particles will be in that configuration. And this is one of the features of chaos and in classical physics. Now, fast forward to quantum physics now, and because the world is fundamentally quantum mechanical, quantum physics must play a role in all this, right? Like chaos, even though it is classical, must ultimately have a rise from quantum physics.
But it's not just chaos, though, right? It's not just a consequence of chaos. It's also a consequence of infinity, right?
Yeah.
Like you don't have to understand chaos to understand that anything that can happen will happen. If you just think about like you have an infinite amount of time, right? And in the infinite amount of time, everything is moving around. Then, in principle, everything you should encounter every single possibility given an infinite amount of time, right?
Yeah.
So infinity plus chaos is what gives rise to this idea. Sorry, continue.
Yeah, but I believe there is almost this slight apparent paradox that kind of shows up, and like we mentioned many episodes ago, that there is a very, very sacred laws in quantum physics, is that of unitarity, to put it plainly, is basically the statement that possibilities are conserved. There are, quantum physics tells you that there are many possible ways that particles can go, but all those must remain. They cannot be created nor destroyed. And so it would seem that if the number of all the possibilities are conserved, then how is it possible for a system to sample all the possibilities when it didn't already sample all the possibilities to begin with? So there's a little bit of a wrench here that I would say even just almost like recently are people starting to grasp a better understanding of that nature. So it's a whiny journey, I would say.
So are you mentioning this kind of discrepancy between how should I say it? Like if I imagine confining particles to one corner of a room and then I release, whatever barriers holding them, they spread apart and explore the entire room, thus increasing like the number of possible states that that can be explored. But in quantum mechanics, states can neither be created nor destroyed. So it's like what gives? Is that the conundrum or
Yes, exactly. So there's a little bit of a conundrum here.
mhm. I see. Yeah, this actually reminds me of like previous episodes of us talking about like the anthropic arrow of time and kind of like all the ways that's an ill-defined thing in terms of subjective notion of entropy based on how you coarse grain the system, as you were mentioning a few episodes back. So I guess then the natural question is like, I mean, it probably seems like you're leading to it. But how do you resolve this conundrum?
Yeah, but I think first of all we need to explain to our reader why that's kind of such a problem. So in quantum physics we have these equation called Schrodinger equation. These are mathematical equations, but the solutions are kind of somewhat simple, at least theoretically. So in quantum physics we have these abstract possibilities, and when you plug into the Schrodinger equation, it turns out that as time goes on, these possibilities kind of go in circles, right? And depending on the energy of these possibilities, the circle radius and how long it takes to traverse them changes. But then, there's this loopy nature of quantum physics. It seems like they all go in circles, right? And if things go in circles, then you say that it will eventually come back to where it started, right? So what gives? We don't see things in our everyday life going in circles, right? Like mention this sentence, I don't repeat it again, given some time later. That does not happen. So what gives? Well, it turns out that in quantum physics, some of these possibilities, because the circles are a little bit incommensurate, like the size of the circles a little bit. So imagine kind of your hands. Like my left hand is going in a circle of a certain size. My right hand is going in the hand a certain size. If they go exactly the same way, my hands will collide. But if one is slightly faster or going in around a bigger circle, then at some point they're gonna get all scrambled up, right? So
you can't do that. It's too hard to do this.
Yeah. So
Tim, quick question: Can you explain what do you mean is going around in circles? When you say like in quantum physics, something is going around a circle. Like, do I think like of a particle moving around a circle, like spinning about itself, or what do you mean by circle? Like, what does that mean?
I think you can think about it like a circle, but I think the more intuitive way to think about it is, Schrodinger's equation is an equation of waves, right? So if we think of matter as waves, right, then there's some periodicity to the waves. Waves and circles are basically the same thing, right? It's just sines and cosines together make a circle. So the fact that matter has a wave-like nature means that the states has this kind of periodicity, and that's what Tim meant by circular.
Gotcha. Okay, continue, Tim. That was helpful.
Yeah. I think that's the perfect analogy. So basically, the universe is a massive wave of many, peaks and troughs going around and around and around. And this quantum picture kind of completely throw the classical picture in a pickle, I guess. Like in the classical picture, you have particles in that's it. Let's say particle in a box that starts at the corner and fills up the room, and then it's like it's never gonna go back to that place now. But here,
no, but it will though. It will though.
It will, yeah, it will. But it will, to the extent that it's very unlikely, but it will. But the quantum physics kind of makes this problem a little more exacerbated, I guess, because the waves itself are periodic in some sense. So kind of individually, the different possibilities are periodic, and the only reason we don't see periodicity is because their periods are a little different. So they're kind of all scrambled up. So I guess the quantum version of that recurrence is that because of this scrambling up, it will, then they're not exactly periodic, but they're not exactly chaotic either, right? Like things that are periodic definitely does not look chaotic, at least in the classical way. So this is kind of a bit of a difference, I guess.
What causes them to have like different like periods? Like what? Yeah, these differences. Like why aren't they all the same?
I think that's kind of to some extent these are the axioms of quantum physics, and that's how we observe the experiment. Like depending on the energy of the system, the periods change, and in fact, if the periods are all exactly the same, I mean, we would live in a terrible world. Like the world would be exactly periodic. Really, recurrence will happen all the time, and it wouldn't be an interesting world at all. Like Mikey, I would exactly predict what's gonna happen, you know, I don't know, in the near future, and then it would just repeat again and again and again without anything interesting. So I guess it's a blessing. It's a mixed blessing, basically, that we have a
But
non.
we can think about this like the simplest case, Chad. The first thing that people learn about in the quantum mechanics course is like a particle in a box. And if you have a particle that's trapped in a box, if it has a very low energy, it's going to have a very large wavelength, a very large periodicity. But if it has higher energy, it's going to have a higher frequency, has a higher periodicity. But what we actually see is kind of a combination of all of these different wavelengths because states in quantum mechanics are generally a sum of all different types of energies, all different types of possibilities. And so when you get all these different waves with different frequencies together, the periodicity becomes very long, the time of the recurrence.
I see. So can we take a step back and like because I feel like now we've gotten to the weeds of recurrence, but like how does this relate to the larger point of what we were talking about in terms of like I guess like the notion of like things in quantum mechanics going on in circles, but things in classical physics not so much.
Yeah, yeah. So one has to keep in mind that even though the world is classical, it's only approximately classical. Like we've known that classical physics is wrong, that quantum physics supersedes. So in some sense, we should just kind of ditch this classical picture altogether the moment we have a better understanding of quantum physics. So quantum physics reigns supreme. Even though we says time is weird in the quantum realm, that is actually the true nature of the universe, right? So now, once we agree to adopt this quantum mechanical picture, now a very interesting question starts to emerge now, because the entire universe, you can think of it as a quantum system. It, perhaps it obeys Schrodinger's equation. And if the universe is like, if these quantum systems are like what we describe, loopy, going around and around, then this raises the question, well, what if the universe is kind of going around and around and around, like I don't know, like a dystopian Black Mirror episode? Like the universe we're doomed to repeat all the mistakes we've made, all the glories and and all the success and failures again and again and again. Wouldn't that be an interesting thought?
I actually that kind of reminds me of a quote by Mark Twain that like history doesn't repeat, but it rhymes. So I don't know if this is kind of like an analogy to this, or
because the fact that it means that there's like these similarities but not exact repetitions. But what Tim is talking about is like literally an exact repetition.
I see.
Yeah, so exact repetition is a theoretical possibility, right? Like I mentioned before, quantum physics deals with all these possibility kind of going up and down at different wavelengths and frequency. Well, what if our universe is just one wavelength? then it would literally be exactly periodic, right? Then the universe would just go looping around and around like a horror movie, or I don't know, maybe like a family movie. Maybe it's not that pessimistic.
Doesn't sound that terrible to me. I don't know.
Wait, okay, so it's actually a few questions about this. What would be the notion of like time in this case? Like, if the universe were exactly periodic, like how would you even measure time in an exactly periodic universe?
So I think okay, I think we have to clarify this a little bit, right?
Okay, okay.
So time, if we think of time as just a parameter going into the Schrodinger equation, then you
Uh-huh.
get a bird's eye view. Yeah, then this whole universe is periodic. You know, it goes again and again and again and again, right?
Mhm.
But if we think of time as what we experience, and we are subsystems of this universe, we don't get the luxury of a bird's eye view. Then our notion of time may, align with this theoretical time as a parameter sometimes,
Mhm.
but not always, right? So
Mhm.
so I think these two different times can be quite different. So and our experience come from the thermodynamic nature, the way entropy is increasing and all that, and so that has to emerge from the quantum mechanical notion of time. So even though quantum mechanics might seem to be recurrent on some level, what we observe is not. So that can be explained, I think, to some extent.
I see. So what okay, so when you talk about time quantum mechanically, are you talking about for like a single particle, or is it like a set of particles, or how do I think about this? Because I mean, if we zoom out, there's all these different like particles on average that each have their own frequency or wavelength that are all combined together and give you
Mm.
this like interesting behavior. When we talk about like what if time were periodic, the universe were periodic, are you talking about like a single particle or like the collection of particles together, or just if there were no measurement made, then this time would be periodic? Or I just want to understand what you mean by quantum mechanically.
Well, I think these understanding in quantum physics is done using very few particles in isolated
Mhm.
laboratory where these recurrence has been observed. Um, and it is, and through those experiments, it is seen that the more particles you add, then
Mhm.
there's more incommensurate frequencies, and the
Mhm.
longer it is that it takes for things to kind of repeat itself, basically.
Mhm.
And as you can imagine, in real life system, just
Mhm.
even after a handful of particles, or even just like a small creature, right? There are trillions and trillions of particles. Even if there was a period kind of there's a periodicity theoretically, that periodicity will be extraordinarily long. It's like way, way, way longer than the age of the universe, right? So effectively speaking, this periodicity is completely washed out in everyday lives. But that
Mhm.
still calls into the question, because time, we believe, is eternal, is infinite. In the
Mhm.
face of in the face of infinity, something very large is still very small. So the
Yeah.
theoretical aspect is what's interesting. That's confirmed by the small number of particles. But the theoretical extrapolation is what's intriguing scientists, I would say.
Yeah, so to break it down, like if you have just one particle, then you have this very short periodicity. You have two particles, circles are not aligned. You have to wait a little longer. Three particles, you have three circles that are aligned. You have to wait even longer. And then if you look at our universe, trillion, 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 trillion particles, you can kind of extrapolate that there would be some enormously long recurrence
Oh.
time.
Oh, that's actually helpful to think of it that way. Okay, I want to ask a slightly technical question just for my own clarity. Is the periodicity assumption true for general Schrodinger equation or only time independent? Like, because if your energy varies with time, then your frequency would also vary with time. It wouldn't
Yeah,
be a constant frequency.
I would say don't worry too much about the Schrodinger equation. Like, it doesn't have to
Okay.
be it doesn't have to be energy. Schrodinger equation is just a generic thing. It does, because space times are all related. You can define time differently. So this definition of time is not exact, but there exists some direction, we believe, quantum mechanically, that things are repeating in some ways. There's this level of repetition, kind of. I think that's the important part.
I see. So Mikey, just to make sure I understand your analogy, if there was only one particle that existed in the universe on average, then the periodicity would be like much less than 2, 3, 4, 5. Is there any, like, I guess, are they like in, I don't know how to say this, like, are they in discrete things, or is there like this continuum of like different like frequencies that a particle can take on, or how do you guys think about it?
That's hard. I mean, if you imagine that our universe is a closed box,
Yeah.
then it would be what you said. It would be an exact. Sorry, what word did you use again?
Discrete.
Yeah, it would be exactly discrete. Yeah. And I don't know. I guess now we're getting into kind of the cosmology of this, Tim. Do you happen to?
Yeah, I mean,
how does our universe compare to like a box? In a box, you have these discrete states, but our universe is not quite a box, right?
I mean, they're different, but probably if you take cosmology into account and kind of believe that there's some quantum gravity coming in, then probably it's discrete in some ways. I would say. Exactly how, I don't know, but the continuum is probably an approximation. But we would have no clue exactly how that works.
It's discrete E.
Yeah, it's discrete T. Yeah.
Even though our universe doesn't have like strict walls, there are barriers that in various places that you can imagine behave kind of like walls, and you get this discrete like behavior.
Yeah, and also beyond that, the time is also not continuous, right? It's probably more like there's the smallest amount of time step, so it's kind of like a frame by frame kind of. But of course, we don't. I mean, I don't know. Let's not delve into the details here because nobody knows quantum gravity, and certainly I don't. So.
But Sahil kind of brought us into like the finale of this discussion, which is the fact that like everything we're saying is possibly invalid because of the fact that the universe is expanding.
Yeah.
All right, I'm glad. I'm glad it brought you guys to the finale.
If our universe was a perfectly isolated box, then what we're saying now would be exactly true. You would definitely have this periodic repetition, exact repetition. And the fact that the universe is expanding, and it's not just expanding, but it's actually like energy is entering into the universe as it's expanding, kind of throws this whole picture into a questionable area.
Yeah, in fact, I think there have been some discussion on maybe even modifying quantum physics to remove the strict requirement of unitarity. Then this whole shebang of preservation of information could be modified. Although
there's been more of a discussion. I think people like Strominger are like they're very certain that unitarity must be relaxed, right?
Yeah, but in any case, yeah, this recurrence could be completely thrown to the trash. If there's kind of this one-way street. And one of these prominent theories that we've described also through previous episodes is this idea that the universe might be eternally expanding, and what we call eternal inflation. It's just expanding and expanding. More space is getting created, and in some sense, more time is getting created. So the more possibilities getting created, and then eventually the universe could be dominated by just quantum fluctuations. So instead of things looping around and around, it's almost like an explosion of possibilities, right? So it's almost like a tree that keeps forking to infinity. And in some sense, that's even more extreme, right? Like now we've traded on these loopy circles to like an infinitely expanding trees that's never ending. So
yeah,
I see.
It's a weird thing, right? Like, so whenever we do these kinds of calculations, when we think about physics, we always imagine that everything is inside of a box. because it's
Mm.
approximately true. I can make a box and I can put stuff in it, and then my theory about the box is true. And if I have a theory about a box, as Tim mentioned, this unitarity principle requires that the number of possibilities has to be conserved. Number of possibilities has to be conserved, then we're going to get this periodic recurrence, and we're going to be here again. But you know, as we alluded to before, there's a growing feeling in the physics community that maybe this is not true. Maybe the rules that apply for a universe in a box do not apply to our universe because of the fact that it's expanding. And so this idea of this periodicity is very much an open question right now.
I see. That is interesting because I'd always thought that unitarity like must hold. That's like the most sacred law of physics, this conservation of information. So now even that is being thrown into question.
In a
Is that
non-expanding universe, it's very, very sacred.
but we are in an expanding universe, so I don't know. I guess
But
I guess
I can draw an imaginary box, and then unitarity holds in that imaginary box. So it's still very, very powerful, right? Like we shouldn't discount the fact that it's definitely not being thrown out. Like anytime you imagine an imaginary box, unitary holds in that imaginary box. It's just that if that box is expanding, then and stuff is entering inside that box.
yeah.
Then,
That makes sense. Okay, so I guess like coming back to this notion of like time going in a loop, or I guess like actually let me ask you this. Like suppose we did live in a box, it's not expanding, and I'm a being that could like exist like forever or whatever. Would I be able to see this like recurrence? Is this recurrence like aligned with the classical notion of recurrence, like particles moving around in a box and then eventually like they all go to the corner of the box? So similarly here, it takes a while for the loop to happen, but once it happens, it like things go back to the original
Yeah,
state things were
I
in.
I would say the recurrence still occurs whether it's in a box or not in a box. The flavor is a little bit different. When things are in a box, of course, there's this periodicity, and you can argue mathematically that if you wait long enough, every possibility you can get as close to it as possible, right? In this closed-ish system. But in the eternally inflating universe, it's a little bit different. But still, because universes keep expanding and spaces keep getting created, time is also getting created. So by chance, you could have these vacuum tunneling happening, just things popping in and out of existence. And at some point, you can create an initial condition that's similar to our universe. And in which case, a new universe like ours in the past could be recreated at some point, because we do have an infinite amount of time to wait and an infinite amount of space to eternally expand into, and time. So in that sense, these recurrence is still happening, but it's just a little more insane in the way that it's exponentiating. Like possibilities are exponentiating more and more and more. So but it is still recurring. If you were a being, it's more like, it's not just that you're watching. I think even you as a being will get duplicated over and over again, watching infinitely many universes doing the same thing again and again and again and again.
That sounds kind of hellish for my human mind.
sounds awesome to me.
Well, Mikey, I'll leave it to you to do that job. Be the watcher of the universe. All right. So So Tim, what you're saying is even in the case of like a non-closed box expanding universe, like eternally inflationary universe like we might have today, this recurrence principle still holds, but it's just that the way in which it recurs is a bit crazier than like a closed box universe. Did I understand that correctly?
Yeah, because it's not just gonna reoccur here. It can reoccur everywhere. It's like you got multiverse now, so everywhere it can reoccur, and there's infinitely everywhere and infinitely amount of time. So it's an more insane version of the recurrence, right?
Oh, that is so. Versus like closed box, there will only be like
There's only
a
one.
single
Yeah.
recurrence. Oh, okay. So either there's like no reoccurrence, or one reoccurrence, or infinite reoccurrences. There's not two or three. It's just one or sorry, not zero. One or like infinite. There's nothing in between. Yeah. Okay. So I guess like okay, that makes sense. So how I guess how does that change how does that change the notion of time itself? Because there's this still like feeling of time moving forward, even as we've been participating in this discussion, time has been moving forward. But you're talking about like loops or recurrences happening in terms of like the states themselves, or like in terms of events happening. But like I don't know, would you say time is a loop because like you can only tell time based on a sequence of events that have happened? And so if it recurs again, then you might as well have started at like t0 at the point in
Yeah.
which it comes back again.
I would say I would say my perspective is that we live in a really weird era of our universe. Like in the beginning of the universe is very quantum mechanical. So these quantum behaviors reign supreme. And in almost like the infinite future, in the distant future, if there's these eternal inflation picture, or these recurrent, I don't know, if we're in universe in a box, it just reoccur again and again. This quantum nature of time also will reign supreme. But it's just really weird that somewhere in between these quantum domination, we have a period of kind of relatively, stable-ish universe where humans can thrive and can make predictions, where we can predict what's going to happen next and all that, and live like a happy life. I think that's the strange part a little bit. Like in some sense, the laws of quantum physics are rather simple, right? Like the complex thing that's going on right now, that's the weird part. Like the world that we are living in, that's the unusual part, I would say. So I think from that perspective, I don't know, like we live in a very special universe.
I mean, if you take a circle, if you zoom into any one part enough, it's going to look like a straight line, right? And isn't that really what we're dealing with here? Like even if the universe is periodic like a circle, it's a massive, massive circle, and we are occupying a tiny infinite piece of the circumference to the point where it just looks like a straight line. Is that not an appropriate analogy?
I would say yes, yeah, maybe somewhat, but this is a way gnarlier than a line, right? It's a line with an earth on it, with buildings and people and creatures and mountains and lakes and the universe basically.
Yeah, but we still perceive like a linear version of time, which I think is a consequence of the fact that we're just tiny.
Yeah, although you could argue from this argument that imagine we are citizens in this vast multiverse. Maybe the entire universe has already gone into this phase of multiverse expanding eternally, right? Then we might be in the serious minority here. Maybe the rest of the universe, the multiverse, the majority of it is just crazy quantum reoccurrence, popping in and out, looping back and forth, quantum fluctuations. And we are kind of in this little corner, just happily be like, living a peaceful human existence without this quantum violence. It's an interesting thought.
Yeah, that is interesting. Yeah, this is a lot to digest. So we're almost at time, so I want to give you guys a moment to say any parting thoughts to the audiences before we head out. Go ahead, Tim.
Yeah,
I
think I mostly summarize it. I think the way we put this title, time is weird in the quantum realm. I think as a physicist, we'll flip this around. Time is weird in the classical realm. At the quantum realm, time is pretty damn straightforward. It's just some waves going up and down, looping around and around. The fact that we don't see that is very strange. So Although we could roughly know why. I don't know, Mikey. What's your thought on that?
Yeah. Oh, I don't know. I don't. I'm just blown away. I just Googled something. Have you seen the show True Detective?
No.
Sahil?
No, I'm not.
Oh, okay. At the end, the protagonist like says this weird thing like time is a flat circle, and so I just Googled it. Did you know that Friedrich Nietzsche also had this doctrine of eternal recurrence?
Oh, is that right?
No.
Not
I
surprised.
think Nietzsche's a dumbass, but like, yeah, I guess. I mean, yes, it's the kind of thing that like you don't even need physics to think about it, right? If you just imagine infinity, it's easy to imagine that all possibilities must occur again at some point if you have an infinite amount of time. And I guess even someone as dumb as Nietzsche was able to come up with this and I don't know, make a doctrine about it. So yeah, and as Tim said, I think like quantum mechanics, what it really does is like it makes it more precise. It makes it easier to prove that this periodicity and this cyclicity occurs. And yeah, I mean that enters into our way of thinking. I don't think anyone really knows what the final story about this recurrence is, but I don't know what I'm saying. I'm not saying anything, man. It's a big mystery, but time is a flat circle, as Rust Cole from True Detective says. That's a fact. What we do with that, I don't know.
That's fair. That's fair. Well, Tim, unless you have anything to say, are you, anything to respond to that about Nietzsche?
Well, personally, I wouldn't I wouldn't make much comments on him because I'm not familiar with philosophy, um, but yeah, I will echo Mikey's statement. At the end of the day, to kind of answer this question requires quantum gravity, and we don't exactly know what that looks like. So stay tuned. I mean, the story could change in the near future, or
People are thinking about it hard right now.
or maybe it will never change. Maybe we'll see you again in eternity plus however many 13 billion years. So
Cheers to that.
All right. All right, then. I want to thank everybody for joining us, and we'll see you all next